So last time we stopped with phase diagrams where you saw a simple question in the quiz, and you should also expect something like that in the exam. So want to start with talking about some of the heat treatments of a steel. You can use different kinds of heat treatment to change the properties of a steel. So you can see that you can change grain structure, remove internal stresses, residual stresses. You can change the ductility, toughness, and other properties. And we have talked about this a little bit before, but we want to talk about it a little bit more in detail. Annealing and normalizing kind of go together, and hardening and tempering also go together. So we talked about annealing before. It is when you have the molten metal and you let it very slowly to cool down. So based on what we have talked about, try to work with your neighbor and write down what you think happens to the material in terms of grain size, strength, and ductility, toughness. So what happens to grain size? What happens to strength, ductility, and toughness? You need to start writing something. I had some in the morning, I gave them all away. Sorry. What happens to grain size? The grain size are larger or smaller? It gets larger. The strength, it's not going to increase the strength. How about ductility? Increases, right? The material becomes softer. And toughness, increase or decrease? Increase. Excellent. So, annealing, other than the things you wrote down, basically you become softer, more ductile. Toughness increases. You have grain growth. And also the residual stresses, which occurs during processing, annealing helps those to be also relieved. So typically annealing is followed by normalizing. Normalizing is kind of a corrective approach. You want to make sure that the strength is still high enough. So after you use annealing to increase the ductility, toughness, grain size, and relieve residual stresses, you follow it up with normalizing. So normalizing, it's more corrective than, let's say, compared to hardening or other strengthening methods. And what it is similar to annealing but at a higher temperature. It kind of gives a little bit higher strength after annealing to compensate a little bit for the loss of strength. And it provides high fracture toughness. We have talked about fracture toughness before. Resistance to brittle fracture. And then the opposite of annealing is hardening or quenching. So take 30 seconds and write down what do you think happens after quenching. There you cool down material very fast. Grain size, what happens? Toughness decreases. The material becomes more brittle. The ductility and toughness decrease. Try to write things down. Then you don't forget. But the most important thing is that the strength is increasing. And this is typically why we are doing it, to make high strength steel. But the material becomes more brittle. And then there is a corrective action followed quenching, which is temporary. So tempering compensates a little bit for the loss of ductility. It is reheating the hardened steel at a lower temperature and increases the ductility. So you kind of increase the strength, then you try to also increase a little bit the ductility so the material is not too brittle at the end. This is how it works. So other than these kinds of heat treatment, sometimes we also add other alloying metals to the steel to change the properties. So it's not only using heat treatment, sometimes you add other elements to change the properties of a steel. So a steel is an alloy of two different elements. Which are those? One, iron and carbon. These are the main components. But sometimes you add other metals. For example, one good reason is to increase the corrosion resistance if you have to use this steel in a highly corrosive environment. Now there is a table in your next slide where you can see some of these different elements, and you see the dosage that you would add them to steel and the kinds of properties that you may expect to get. Try to see what you have to add to your steel to get corrosion resistance, for example. So if you see at the end of the last slide, I have a question mark. So what element would you choose from this table to make, for example, the steel corrosion resistant? Copper? Chromium. Oh, okay. This is also, it also works. Yeah, why not? Atmospheric corrosion resistant, because normally we use chromium, so I actually didn't see this. Yeah, so for example, chromium or copper. Here, chromium is more typical. So you can see that there are other sorts of properties that you can promote by adding other elements. I don't go through it. This is a table. You can go and check it out. So sometimes you add other elements. And I'll show you that when you buy a certain type of a steel, you kind of know the composition. They give you what type of alloying elements you have and what type of properties you can expect. Okay. So now I want to kind of go through different types of steel and tell you about different applications they have and what type of properties you can expect, etc. So it is very descriptive. We'll try to go through it as quickly as possible. It's not difficult. It's very simple. So we start with low carbon and medium carbon steels, which are normally used for a structural steel. When I say structure, I mean more like load-bearing members. And why is that? This was your quiz. Yes?
They're more ductile, so they can take some deflection rather than immediate failure.
Exactly. If you wrote that in your quiz, you get full credit for that problem. So the reason for that is that they are more ductile. And they can absorb more energy before failure, and this is what we favor as structural engineers. And high carbon steel also has some applications in civil engineering. For example, pre-stressing elements. You normally want to have high stress reinforcement. And then there are other kinds of steel that may be used in non-structural components. And we kind of want to go through these categories one by one and kind of get an overview of what is going on within each category. Starting with low carbon steel, which is super important for us as civil or architectural engineers. Of course, as the name suggests, the amount of steel is very low. It's less than 0.25% of weight. You see one example here, so really load-bearing structural elements. This is a beam or a girder. I don't know exact size, but you can see that this is made of low carbon steel. And always remember that the reason we like them is because of their high toughness and high ductility. The yield strength is about 40 KSI. The tensile strength can be up to 80 or even sometimes 100 KSI. These are cheap types of steel, another good reason to use them. And they're used for structural shapes, something that we care about. If you were mechanical engineers, you wanted to know that they're also used in automobiles. And sometimes you add other elements to improve the tensile strength of these steels. So these are a few facts about these steels. And it's kind of, I told you that steel is not like concrete. We don't, as civil engineers, we don't really make it. We basically buy it from a catalog. And the catalogs look like that. They are not as colorful as shopping catalogs. They look like this. They give you, depending on the society or the convention where they are being defined. For example, American Iron and Steel Institute, AISI or ASTM, American Society for Testing and Materials. They have different designations. One very important, famous kind of a steel that we use very often is this A36. And you can kind of see in the catalog what are the elements in the composition of this material. And for the other types, you can also go and check. You see that the carbon percentage is 0.29% weight, for example. And then you see that there are other elements. And these kinds of codes also provide you with the approximate or typical mechanical properties of the material. So for example, you know if you choose A36, what type of tensile strength and yield strength you would expect, or what would be percentage elongation. So you kind of decide on what type of properties you need, and then you go to the catalog and you search for the right type of material, if you want to imagine how the design process works. Questions about any of this? This is again ASTM designation. You can see here again, this is yield. This is tensile strength. So in the code, you have these kinds of tables where it tells you if you choose this type of a steel with what grade, what type of material properties you can expect. Exactly. And the composition. This is pretty much the same thing as I told you before. So a lot of times you treat, as I told you, the low carbon steels to get higher strength properties. So this plot is kind of important. So we are looking at here A36. you see that the ductility is pretty large. The strength is pretty relatively low. And then this is another type of a steel which has a little bit higher a strength. It has a higher yield strength. And then interesting one is the third one here. So this is heat treated, is quenched and tempered. And look what happens to the stress strain diagram. You see that the slope stays the same. We have the same elastic modulus, but you see the yield strength has moved up quite a bit, and the tensile strength has become much higher. So you may see, like if I give you a stress strain diagram, and I just tell you what happens if you heat treat this steel, let's say using annealing or quenching, then you should be able to draw the strain diagram for the heat treatment. And it's kind of easy, right? You know that already what quenching does. It increases the yield, increases the tensile strength, and it doesn't change the elastic modulus. So heat treatment doesn't change the elastic modulus. If it is not written here, we can write it. So it does not change E. What it does is increasing strength and yield. Any questions about this? And at the same time, you see that the ductility has decreased quite a bit. It turns out that different types of low carbon steel, they also have different behaviors. For example, if they're exposed to very high temperatures. Last time I told you, a steel has two big problems. One is, what are the two big problems of a steel? Exactly. Corrosion, you saw that you can add many alloys. I'll show you some other tricks how you can have a corrosion resistant material. For fire, you kind of have to know what the behavior is. So here you can compare different materials. Let's say our favorite A36 is this one. So you see that it doesn't lose the strength as quickly as, for example, this other one. If you compare A588 and A36, A36 is behaving a little bit better. It takes a little bit longer for it it takes a little bit higher temperature for it to lose the same amount of yield strength. Any case, this is, I thought to show you that also. And now we can move to medium carbon steel. So low carbon steel, medium carbon steel. And of course, medium carbon steel has a little bit more carbon than low carbon steel, as the name suggests. We don't expect anything different. And it's typically obtained using heat treatment, quenched and tempered, and it can have other elements. What is important is to pay attention to the applications. Sometimes in some structural components, if we need really high strengths, we may use medium carbon steel, but kind of a very important application are in the railway industry, as the picture also here suggests. There are also codes and standards for this kind of a steel. I want to show you. Sorry, sure. Again, we don't make them, so we kind of have to live with what is in the market. This kind of a steel has a different naming, which depends on the type of standard you're using. In terms of applications, it's important to know that sometimes we use it, but mostly like in railway industry especially, they use high strength steel, medium carbon steel a lot more. Should I move? Everyone has everything later. Yeah. So just that you see, there is no reason to memorize this or anything, just to be familiar, is the designation of the names looks something like that. For example, here 10 is for plain carbon, 11 is for free machining, and then this XX gives you the amount of carbon. So if you have like 1040, it means that you have 0.4% carbon, something like that. And there are tables like that issued by different organizations where you can see the properties of different steel. Think about it as catalog, really. You have catalog for materials for steel to choose from. Here, the same kind of thing, but instead of seeing the composition, for example, for 1040, you can see the tensile strengths. Pay attention that this is much higher than what you saw in low carbon steel. So now the strength is up to 120 KSI compared to 80 maximum. Yield strength is up to 85. You have ductility. It can be varied, and then you see here the applications. So low carbon, medium carbon, high carbon. These have much less applications in civil engineering, but sometimes it's being used for reinforcement. The amount of carbon is much higher, and they are very wear resistant. That's why they are being used for cutting tools. And sometimes you may hear that they are called two steels. What else? You can add other elements to improve the properties. They are very brittle, of course, but the strongest. This is kind of obvious. I hope that I have emphasized this so much that I'm sure everyone remembers that. High carbon steel, you again have a different type of designation. You can look up the tables, and then you see the composition, you see the applications, etc. And you can also see the properties. I don't have a table for that, but one type of steel that you may be familiar with from household goods, sometimes reinforcement also. So this is a steel reinforcement. Is a stainless steel. And why it is good? It's because it's resistant to corrosion. And you saw that like one way to do that is add chromium. And this is basically what it is. It has a lot of chromium. Of course, it's great, it's corrosion resistant, but the caveat is that it's very expensive. So you cannot really have bridges and highways having all stainless steel reinforcement. So cost is the major disadvantage. Here are, again, classifications. You can look up from the number. These are in codes. These are just examples for you to kind of see what is going on. You can see the material properties, and you can see the types of typical applications that you may have. Any questions about any of that? It's very descriptive, so I'm going fairly fast. The same here in terms of material properties. So what you have is that you have codes with tables inside. Once you want to design a steel girder or a beam, you figure out what you need in terms of yield strength, in terms of tensile strength. Then you go to the code and you look out for the right material, which has the lowest cost but gives you these properties. when you take other classes, like in a steel design, you are going to learn how to do that. Now, one thing is very important is that we don't like to see steel reinforcement to get corroded inside the concrete. You all have seen the steel reinforcement in concrete. So anyone who hasn't seen it? Great. So next time you see a job site, try to pay closer attention. Make sure you look at what type of steel reinforcement they're using. And it turns out that there are other ways to increase the resistance to corrosion. One is to use galvanized steel, which is basically you dip the steel into zinc, molten zinc, and it generates a protective layer around the steel that prevents corrosion from happening. And the other one are these green kind of reinforcement. Have you ever seen the green reinforcements in the job site? Here, this is an example. I know the light is yellow, so I'm not sure if you see the green here. But they have a distinct green color, which you have seen. And so this is how the mesh looks like before pouring concrete. And this is also helping with corrosion resistance, because you have a layer going around the steel and it prevents corrosion from happening. Now, why do we care about corrosion so much? Why? What happens? Yes, because of failure of concrete. I remember that there are a number of people from Pittsburgh here. So if you go to Pittsburgh, sometimes you look at the concrete bridges, the deck, you see the spots where the steel is corroded, it's completely orange. And then what happens is when you have corrosion products around the steel, they take the space. So they push on the concrete, they create cracks, and then a chunk of concrete gets basically, it just falls off. You have a spalling, right? So that's why we don't like to have corrosion. If you go to Toronto, for example, you see this all over the place. And why do we see that in places like Pittsburgh or Toronto? Yeah. No, that's not the reason. You can have freestyle because of that. But what is the problem that you have this much corrosion? Exactly. So during the winter, when there is ice, what happens? They come and they put a lot of salt on the road, and the salt gets into concrete and it makes the steel corroded. So that's why you have to come up with all sorts of tricks to try to prevent corrosion from happening. It would be great if you could use stainless steel everywhere, but it's not economically feasible. The problem with these solutions is that they are great if everything is perfect. But if during the construction or handling, let's say a piece of the epoxy gets broken, that point becomes very susceptible to corrosion. So from there, the ions, they can go inside and they can create corrosion and damage. So these are good practices, but we need to be handled very carefully to make sure that you don't have any wearing, it doesn't wear off the material. Okay? The hot rolls, the steel that you get from the plant, the hot roll sections, these are the typical hot roll sections. So I don't know if you have seen this in the job site, so you have paid attention. Like beams and girders are typically W or S, for example. You can have angle with equal or unequal legs. And if you cut one of the W sections in two, you get this WT section. And you have this C section or channel. Sometimes you see like channel in trusses that they're being used. So I have some more pictures here. So this is how They could look like I-beam for obvious reasons. It's called I-beam, white flange. And you see these different kinds of profiles that you can get from the factory. And civil engineers or architectural engineers, I notice classes mix, they have some shorthands. So, for example, if someone is talking about W27114, that means the W section, which is 27 inches deep, and the weight is 114 pounds per feet. So the weight is always expressed in terms of the amount of weight per unit length of the beam. And then there are other ones. I just put this here as some examples. Like when you go to your structure, steel structure class, kind of have seen one before. What is it? I upload this complete slides so you can have it. Don't worry if you haven't written down everything. If you take a steel structure, you will be working with AISC manual, which is American Institute of Steel Construction, and where you see all tables, long tables with these profiles, with their properties, and when you design, you go and pick up the right profile and stuff there. These are hot rolled sections, as I said. Don't worry if you don't have everything written up. I'll upload these slides later. And then you can have cold form steel, which is basically cold rolled and pressed. And this is typically causes having higher yield and lower ductility. And they are normally non-structural elements. They're used for floors, walls, roofs. And these are some of the examples of that, like a kind of a channel. Question? Oh, sure. This fine? So it's good to distinguish between hot rolled and cold rolled products, and kind of have an idea, understanding of what is hot rolled, what is cold form when you go to the job site looking at different elements. It's good. Yeah, these are some of the examples, just that you see. And finally, reinforcing a steel. So this is how it looks like during construction. In the past, we were using plain bars, which is like a smooth bars. But now, typically, we use deformed bars, which have threads. And this is for the steel to have a better bond with concrete. This is one type of reinforcing steel. The other type are pre-stressed steel for pre-stressed concrete. I wish I had a picture here because it's hard for me to draw it. But here you basically have a number of steel kind of ropes which are they're twisted around and you have it inside tandem. And they're used for pre-stressing. This type of a steel has to have higher strength and low relaxation. What is relaxation? You still remember? Relaxation? Exactly. When you keep a strain constant, a stress decreases. Remember when we were learning about viscoelastic materials? You want this material not to lose a stress. So you want it to have low relaxation. You don't want it to lose a lot of stress because it is a pre-stressing element. If it loses a stress, it loses functionality. You put concrete in in compression, so that if you apply tension, it doesn't feel the tension. So you put compression in the beginning, the concrete is under compression. So even if you apply tensile force, it's going to be neutralized by this shear stress compression that you apply in the beginning. Since you haven't taken any of these classes, it's hard to explain exactly what it is, but I hope that you have some ideas, and I have explained this when I was teaching relaxation. So this is one example where you have to use high carbon, high strength alloy in our applications. But in typical construction like buildings, etc., you use reinforcing steel bars, the deformed ones, and this is because you want to ensure you have a good bond with concrete. They have threads. If next time, if you have never worked with them, when you go by some job site, pay attention. They have some threads and they kind of they bond to concrete because of that, so they don't get detached very easily. So concrete and steel works as one unit. Is this clear? When I say good bonding and they work as a unit. You all have seen reinforcing steel at some point in your life. Great. I never knew. And the designation of these bars are typically you start with the plant, steel plant, and then this is the bar size. In the US, if you take the bar size and divide it by 8, it gives you the diameter of the bar in inches. So it's kind of a convention that we have. And then you have some other letter which kind of specifies the type of a steel. And then you have the grade for that steel. And what that means is that when you have higher grade, these are some examples of the types of steel. If you have higher grades, you have higher strength and less ductility. And there again in the code, there are tables with the properties of different types of reinforcement of steel. So when you get to the point that you are designing concrete and you need to specify the type of reinforcement, then don't worry, there are manuals and codes and tables that you can go and pick the right material. Questions about any of this? Let me go back quickly here, and you see here the type of a steel, let's say, is here, and then you have the grade and the properties. Great. So basically, as usual, we have the name of all the figures. You need, when you review the material, especially for this exam, make sure that you can answer all these questions. Now we don't have time to do it in the class. And as usual, I have a list of buzzwords that again you need to make sure you know what these are and you can explain.